Hello everyone, welcome back to this lecture number 2. In the previous class we have discussed different logic gates and their truth table. In this lecture we will be talking about different laws of Boolean algebra. So before discussing the laws of Boolean algebra, let us revise different Boolean functions of logic gates. So we have talked about AND gate, OR gate. Let's say this is AND gate and it is having two inputs A and B and it is generating Y. If we represent this Y in terms of the Boolean expression, Y will be represented as A dot B. This is an Boolean expression, right? Similarly, we can write the Boolean expression for OR gate. Let's say it is having input A and B and Y is the output. So the expression for OR gate will be written like A plus B. For NOT gate, let's say A is the input to an inverter or NOT gate. So simply we can write A bar, or in some of the books you may see like A dash, like this, right? Now if it is NAND gate, like this, the symbol of NAND gate is, we have already talked about. Input I am considering again A and B. Output is, let's say we are considering Y. Don't get confused. This Y and this Y, you consider different things. Okay. Otherwise I need to consider Y dash. Okay, so just consider this is the output of any NAND gate which is having input as A and B, right? So this Y will have the Boolean expression like A dot B whole bar, because it is the negation of AND gate. Similarly, when you talk about NOR, the symbol, the representation of NOR will be like this. There will be a bubble. It is generating one output, taking input like A and B. The Boolean expression for this we can write like A plus B bar, right? In terms of XOR we represent like this. There are two input A, B, and Y is the output, let's say. So XOR will be represented like A bar B plus AB bar. This is the Boolean expression. We also represent A XOR B with this symbol. So I guess you all must be familiar with this, right? For XNOR, the representation is almost similar. We just put a bubble, and let's say if Y is the output of this XNOR gate, it will be represented like AB, or you can say A bar B bar, or we can write like A dot kind of, right? So these are the representation and the Boolean function of these. We may have any kind of circuit in digital electronics. The circuit's outputs can be written as a Boolean function, and the functions can be minimized. So in order to manipulate the functions, we need to be very much aware about the fundamental laws of Boolean algebra. So let's discuss the laws of Boolean algebra. So let me clear all this. Okay. So there are different fundamentals laws of Boolean algebra. Let's talk the very first thing. In case, let's say we are having AND gate, and this AND gate I'm passing, let's say, A and A input. In that case, this will generate A dot A kind of output. So if A and A is high, let's say if I talk in terms of the truth table, A and B, I'm assuming there are two inputs. Y is the output of a logic gate, which is AND gate. So let's say if this is 0, 0, 0, 1, 1, 0, and 1, 1 kind of truth table, right? Now when we give both 0, it will give us 0, and when both 1, it will give us 1, and here let's say it is 0, 0, right? So we are just focusing these two cases here where both the inputs are same. So if we are giving 0, we are getting 0, and when we are passing 1, we are getting 1, right? So that means if it is A dot A, it is equivalent to A only. So that is the very first law you can consider. If let's say A dot A is returned, it is equivalent to A. Similar thing you can assume that if let's say A or A is returned, how we can convert it? Same thing, like this time I'm considering we are having OR gate because plus represent OR, and I'm just drawing a truth table for OR. So if it is OR gate, let me convert this gate into OR gate. So let's say this is OR gate, it is generating output Y, and both the inputs are same, A and A. So let's see the scenario. If this is the truth table for OR gate, generally it will give 0, then 1, 1, 1. So this is two input OR gate truth table. Now let's focus on wherever we are having high or low, the similar kind of input. So if it is low, both the inputs are low or high, we are getting the same output. So if it is low, it will give you low only. If it is high, it will give you high only. So that means here also we can write A or A will give you A only. I hope it is clear, right? So this is the very first law you can consider. The next law, let's say we are having one input X and we do ending with 0. Now if you apply this logic with the help of truth table, you will get that when you do this, you will always get 0. Okay, so if you want to draw the truth table, that is quite easy to draw it. So I'm not writing the truth table for that. I hope you can understand this. Similarly, if you write, let's say, x plus 1 or x or 1, x is one of the input. So I'm assuming there is a two input OR gate. Let me clear this. So I'm assuming here there is two input OR gate. One input I am passing as x, another input is high, that is 1. Now we are trying to predict this particular output. Okay, so this x can be two things only. X can be either 0 or 1, nothing other than that, no other value than 0 or 1, right? So in case x is 0 and this is 1, you will get 1 here. In case x is 1 and this is also 1, so like a plus a, it will give you a only. So in both the cases we are getting 1. Hope you are getting. So you remember this thing as another law. Now the next thing in the Boolean algebra, let's say we are doing, let's say there is a Boolean variable x, and let's say on this Boolean variable you are complementing it, right? So complementing, we represent the complement by a bar or dash. So if we are complementing it, if we double complement it, then it will become x only, right? So if we double complement, then in that case it will become x only, right? Now let's say we are having two input logic gate, like one input is a, we are having OR gate, another input is b. In case we change the input, instead of a we will give b, like here, assume that what I'm saying is here we are passing a and here we are passing b. In case you change here b, here a, then also the same y you will get, right? So a plus b or a or b will give you b or a, right? Like commutative law, I guess we all are aware of it. Similarly, if it is a dot b, it will be always equivalent to b dot a. It is also like commutative property, right? Right now, few more properties. If we are having, let's say, a dot 1, the meaning is there is an AND gate, it is getting one input as a, another input as high 1, then what will be the output? So if you test this through the with the help of truth table, a can be, you assume, like either 0 or 1. So when it is 0, it will give you 0, when it is 1, it will give you 1. So that means it will always be dependent on a, right? So it depends upon a only. If a is 0, the output will be 0. If a is 1, the output will be 1, right? Okay. Now there's one interesting law which we consider as Demorgan's law. What Demorgan says that, let's say there is a or b and you complement it. If we do so, we can write the same thing as a complement dot b complement. Okay. If we complement a dot b, then this thing will be equivalent to a complement or b complement. Okay. Now there's another thing. There are certain more properties you may be familiar with. let's say if we are having A and it is having, let's say, dot operation with B or C, this thing can be written as A dot B or A dot C, right? So this is considered as distributed. Okay, right? Sometimes these bar may be represented in with different symbols in different books. I hope you can understand all these things, right? So with this, I'll end up this lecture. We'll solve the problems in the class. Okay, thank you. See you in the next class.